Hey everyone, welcome back to the channel. It has been a while since I've recorded, so I might be a little bit out of practice. One thing you may pick up on is my stunning goatee, which I've actually developed because I was getting hit on by too many baddies at the gym. It was getting distracting, so, had to nerf myself. But it's a Saturday morning, it's snowing outside, and I've got nothing better to do than talk about some systems design, so let's go ahead and get into it. Today we're going to be building a rate limiter. Alright, so a rate limiter. What is it do? What is it meant for? Let's go ahead and quickly provide an example. Here is myself. Let's imagine that I am feeling like my YouTube videos aren't getting enough views because they're cracked. So I go and watch my own video times 1,000. I literally just open up a bunch of tabs on my browser, I'm logged in, and I go watch my own video 1,000,000 times. And all of these are resulting in me getting another view. Well, YouTube doesn't want me to do this because not only does it have to pay me ad revenue for all of those, but also it's just incorrect. So they say to me, guess what, buddy? You can't account for all of those views. We're actually going to stop you from watching even more videos. Now, this is a kind of convoluted example because I don't really think they would rate limit your viewing, but they might rate limit certain other endpoints. The gist is eventually the server is just going to be like, hey, you've done this too many times, you need to take a break, we'll tell you when you can do it again. So the API is going to respond with like, no, you can't do it, you're getting rate limited. Cool. So let's outline some formal problem requirements now that we've gone through that. So number one is that we basically are going to be building a rate limiter that's going to stop bad users, malicious ones, or potentially just negligent ones from submitting too many requests. Like I mentioned, that can easily bring down your service. You want to stop this from happening. It can add extra load on your service too. Additionally, this rate limiter should introduce minimal latency, meaning we want to make it as fast as humanly possible. Every request has to go through this rate limiter, and as a result of that, we really don't want to be introducing a ton of extra latency here. It is going to kill our user experience if we do. Another thing is that there are a variety of different rate limiting techniques. Let us try and support at least a couple of those. Now, for what it's worth, at least from what I understand, there are some pretty complicated rate limiting algorithms. I'm not really going to go into anything too crazy here, simply because I just don't think that's what fits in a systems design question. If you get cut in an SDI because the interviewer is like, you need to describe token bucket rate limiting, I don't know, seems dumb to me. I feel like it's more so about the actual architecture of it rather than the algorithms, but we'll do a couple. Okay, so let's do some quick capacity estimates because this is going to be relevant in terms of whether or not we need to actually partition out our system. So let's imagine we've got 1 billion users that are using our rate limiter. I mean, that would be great if our site had 1 billion users. And imagine that we had 20 different services to rate limit. So when I say 20 services, that could be endpoints. They might be authenticated or non-authenticated. So it might be the login endpoint or the create user endpoint. But it could also be something like, make a post endpoint or read a comment endpoint. So let's imagine that for every single user ID, that's like a long, so that would be 8 bytes. And then additionally, if we want an integer to keep track of how many requests a particular user has submitted, that would be 4 bytes. Now in reality, we're probably going to need more metadata than just a single integer to keep track of request counts, but I'm just trying to get a general estimate here. So assuming that we multiply all of those things together, right, we've got 1 billion users. For each user, we need to keep track of their count of requests for 20 services, and then for keeping track of those counts, we need about 12 bytes. That means at minimum, we're probably looking to store at least 240 gigabytes of data. So keep in mind that we want to have minimal latency here. If we were thinking about an in-memory solution, 240 gigabytes is probably too big to be storing on one node. There are some servers in memory that have 256 gigabytes, but again, this was kind of an estimate. You'd really be pushing it if you did that. So again, if we are planning on storing things in memory, we're likely going to need to partition out our server. Okay, so now we've got a more general question, which is what do we actually want to perform rate limiting on? And we've got really a couple of options here, at least that make sense. You can perform rate limiting on anything, but it's probably better off that I'm not performing rate limiting on like the actual type of request that you're making and more so something about you as the user. So option number one would be the user ID. The good thing about this is that it's pretty easy to track. It's probably being passed in every single request, and that if we have a malicious user, we can block them. That being said, it's not perfect, right? If I'm a user at home and I create many accounts, well, the rate limiting on one user ID is now not going to work as well. I will basically be able to submit as many requests as I have accounts. Additionally, not all services need authentication. So if I have a login request and someone wants to DDoS that by just spamming it 1,000,000 times, I have no user ID to rate limit that on because they're not logged in. They're trying to log in, they're using the login service. So I guess the fallback option would be the IP address. So the nice thing about this is that, if someone is creating a bunch of accounts over the same network, it's easy to track. And in addition, it doesn't require being signed in for actually rate limiting a given endpoint. The bad issue here is that you can have false negatives, basically saying, I'm going to rate limit you, but, I've done nothing wrong, and it's my brother on my internet who's, being the bad actor. So you don't always want to have to throttle that person, but it's perhaps better to be safe than sorry here. So sometimes you do likely want to use IP address. So ultimately, I think something like a hybrid approach makes the most sense, where you use the IP address of a user on non-authenticated endpoints, and then the second you're logged in, you can go and use that user ID endpoint. So hopefully that makes a bit of sense. Let's quickly describe a rate limiting interface. So the gist that I mentioned is that we may have multiple rate limiting algorithms of how we want to limit the number of requests a user can make. Because they're going to have different implementations, what is the interface that actually describes how it works? So it should be pretty simple for the most part. We've got this function rate limit, which is going to return a Boolean, which will be true if the request should be throttled or rate limited, and false otherwise. That's just going to take in a user's user ID, their IP address. The user ID, I suppose, could be nullable, right? Because if it's a non-authenticated endpoint, you're not going to have that. An IP address, a service name, so this would be like, make post, because every single endpoint should probably be rate limited separately. I suppose you can make the argument that you can rate limit a user, all at once, but I think it makes sense, at least for now, to do it separately. And then also a time of the request, because typically we're performing rate limiting on the actual amount of time between requests. I suppose that if it's a service where you have an API key and you just want to stop them from making a certain amount of requests total, because they've run out of request tokens or something like that, that would be a little bit different, but I'm assuming this is all going to be time-based. Okay, so another question now that we have to ask ourselves in terms of discussing architecture here is, where within our system does the rate limiter go? So again, we do have a load balancer, right? And I'm assuming for now that the load balancer and the rate limiter are separate entities. However, it is possible that if we want to make minimal network requests, we could actually put our rate limiter on our load balancer, right? Well, maybe not, because we mentioned that the amount of data that we need to store is probably going to be too big to keep in memory, thus making it infeasible for our load balancer. Could we put it on our load balancer's hard drive? Maybe, but then now all of a sudden you have a disk access, and that could potentially be very slow. You don't always want that. So option number one is we could perform the rate limiting locally on every single service that needs it. So imagine we've got a make post service, and then, a get comments service. You would actually store in memory some data about all of the requests that users have made, so that you can go ahead and perform rate limiting locally on the server. So that's option number one. And number two is going to be the dedicated distributed rate limiter. So that would be rate limiting basically as its own layer in our system. So we'll talk about the pros and cons of both, starting with the local rate limiting. So I'm going to just call this service local rate limiting. I don't know if it's a real term. I'm making it up right now. So maybe don't use it in your interview, but hopefully it makes sense. So the pros of this should be somewhat clear, which is that there are no extra network calls required. Because all the rate limiting is done right here on our service, we can just keep that data locally. And as a result of doing so, we are in good shape. Okay, so no extra network calls. However, there are some cons, besides the fact that now you don't have to actually manage a distributed rate limiting layer. Number one is that if we're getting spammed over and over again, and this is a really big point, those requests are still making it over here to the service, right? And so that's going to use up a bunch of network bandwidth. We don't have a separate layer that's kind of eating up those requests and making sure that they don't get put on our service. Okay, so that's one aspect of things, which is that we can use up the server network bandwidth. Another one is basically that our application and the actual rate limiting scaling are tightly coupled. So what I mean by this is, let's say that this amount of storage right here is not enough. So we need more rate limiters, right? I'd now have to create a second replica of service 1, service 1 replica 2, just to store all of the rate limiting information. And to be honest, that might not necessarily be useful, because who knows, we might just not need that much capacity in terms of dealing with all the service 1 requests. It just so happens that because of the need to be able to rate limit, that we have to scale it out a little bit more than necessary, which is not necessarily that useful. And then lastly, of course, if one of these guys were to go down, we lose the rate limiting information with it, which is not the end of the world. The user can just make new rate limiting requests when it comes back up, but it is worth noting that that happens as opposed to a dedicated distributed layer. So let's go ahead and talk about that. What would that look like? So here we would have our load balancer, and basically on every request we would first reach out to the rate limiter. The rate limiter would say, okay, this request looks good, I'm not rate limiting it. And then number two would be we actually reach out to our service. So what are the pros and cons of this type of approach? Well, the biggest pro is that we actually shield our application servers from large bursts of network traffic, right? If I'm spamming, spam, what's going to happen is the rate limiter, instead of saying okay, is going to say no, you're not getting through, and then there's not going to be any part of this. We're never reaching out to our service. Now, of course, these are still going to hit the load balancer, which is shitty, but eventually there's not really much you can do about that. So again, that's one aspect of it. And then another thing is that we scale this down, up or down independently. So if I need more space for my rate limiting information, I can just do that. Rate limiter, rate limiter, rate limiter. And I can, partition these by users or something, and our load balancer can keep track of which rate limiter to actually reach out to. So again, that is totally doable. And then now, we can only keep one instance of our service. We don't necessarily have to, make 4 of them. So of course, the bad part of this is that now all of a sudden we have to make an extra networking call to our rate limiter, and that is going to slow us down. We don't want that. Well, what could we potentially do to make our life a little bit easier? One thing that we could possibly do is actually doing some caching. And where would we do it? Well, in a place that is going to allow us to avoid an extra networking request, which in this case would maybe be the load balancer. So what could we do? Well, basically we could have the load balancer effectively be a write back cache. And what I mean by that is that after a certain point, the load balancer basically acts as a partial rate limiter itself, but just not for every single user ID, only for certain popular user IDs. So maybe if we have, a rate limit of 10, what we could say is that when the load balancer receives from the rate limiter that there is someone who's made 5 requests within a certain time period, that it'll actually cache that value. So now all of a sudden it's storing that I've submitted 5 requests. As you can see, it's going to store that over here. We're going to cache it. And the next time when I reach out saying, hey, can I make this request? It already knows that I've made 5 requests. It can locally add such that now it sees I've made 6 requests. It can say okay, and then I can reach out over here. So this will ensure that certain particularly spammy users aren't even making their way all the way to the rate limiter, but are just getting rejected on the load balancer. Again, it's not really even important that all of this stuff is getting written back to the rate limiter in our write back cache, assuming there's only one load balancer. If we're using something like an active load balancer configuration, then we may run into a few more problems, and we have to be a little bit smarter about how we'd actually partition our requests to load balancers or something like that. But assuming there is just one load balancer, this approach can work very nicely. Okay, so let's now discuss our database choice. So we know that our rate limiter is going to be a separate service, right? And the question is, how can we basically set this thing up to be as fast as humanly possible, both for reads and writes, because otherwise we're really going to be slowing down every single request. So the idea is we want them to be as fast as possible, and as a result, we probably don't have time to access disk. When you want to keep things fast, disk really can get in your way. So what can we do? We could just keep all of our data in memory. So that would naturally lead us to either A, just using our own custom application server solution, or B, employing something like Redis or Memcached, which are both just in-memory databases. So personally, I lean towards using Redis here just because it's got some existing data structures that we could use, like a list or a hash map or anything like that. And then also, as far as setting up replication goes, there's not much that we have to do on our end. It takes care of a lot of that for us. Pretty easy to get single leader replication going. So I personally am leaning towards Redis. I think if you want to make the argument for any other database that stores stuff in memory, be my guest. Okay, so now let's talk about our replication choice. I guess the question is, can we get away with using something like multi-leader or leaderless replication here? That's a good question. At the end of the day, we do need our rate limiter to be fault tolerant, because if one of them goes down, that would mean that all of a sudden we can't submit any requests to our service, and that is unacceptable. So let's think first about multi-leader and leaderless replication. Imagine we have multiple rate limiters, RL, and basically, they're in a multi-leader setup where they're both communicating with one another. First of all, that could increase our write throughput because now writes can go to either of these replicas. And additionally, it could even decrease our write load on each of those databases as a result because, now I just have more places that I can write. At the same time, though, let's say a rate limiter thinks Jordan has 3, and this guy thinks Jordan has 2. We need some time for them to actually sync up. We have to wait for anti-entropy, and there's not really any guarantee on when that would happen. Another aspect of things that we could do is use a CRDT. So again, this would be more of like a version vector almost of counts that I've done. So this guy would say, I'm replica 1, so I believe that I've received 3 writes, and replica 2 says I've received 2 writes. So basically my count is 2 locally, and then my count is 3 locally over on the left here. And then when they sync up, this vector becomes 3, 2, which is going to indicate that we have a count of 5. So that's what a CRDT is. It's basically, the idea is that even though locally, we don't have the right answer, when they eventually sync up with one another, they do so in a way that doesn't cause any write conflicts, and we can actually get the total number of times that I've submitted a request. Even still, again, I think it would be better off to just be accurate in our rate limiting counts from the get-go, and the way that we can do that the most easy is by using a single leader. So again, if we just have a single master node, RL right here, and that's got something like a follower, if I write to the master node, this is going to be asynchronous over here to the follower, and then I can always just make read requests from the master node as well. And if this guy goes down, then this guy becomes the master. Now you may be saying, well, what if we read from all the followers? We could, but we might get stale reads. And then you might say, well, shoot, now the master is going to have very high read load, and you'd be correct there, but I guess we could just create a sufficient number of partitions such that hopefully that isn't an issue. So that is my thinking there. But moving on, now hopefully we can get to the actual meaty part of this video, which are a couple of the algorithms that we want to be implementing. So I'm going to be talking about 2 in this. There's fixed window rate limiting, and then there's also going to be sliding window rate limiting. But these are relatively basic. I've actually spoken about how we might implement these types of things in our stream processing video. So if you need more detail on this process, you can go ahead and watch that. But the idea here with fixed window rate limiting is basically that we have a certain rate limit, let's say it's 2 in this example, and that it resets every single basically discrete unit of time. So in this case, let's imagine that it resets every single minute, starting from, like a new clean minute and going to the next new clean minute. So for example, that means that these 2 requests are valid. Now at 101 we reset, so these 2 requests are valid, and oh shoot, this one comes within the 101 minute, so that one we have to rate limit. So to keep this in mind, imagine, we're storing the following data structure, right? We have some map from service name, which is going to be upload, to user ID, which is going to be 22, to basically the current time and the current counter. So at 1 o'clock so far we've got 0 requests. So this guy comes in, now all of a sudden we've got 1 request at that minute. This guy comes in, now we've got 2 requests at that minute. This guy comes in, now we're down here. We have 1 request again, but the time is now moved up to 101. Same thing for the next guy. Now we've got 2 requests and the time is moved up. And then finally, when this erroneous request comes in, or not erroneous, but we have to rate limit it, this comes in, the counter gets set to 3. You can see that that is bigger than 2, and so now all of a sudden we have to actually throttle that client. So hopefully that makes sense. I'm going to go through the actual pseudocode for it really quick, but no worries if the above just made sense and then the pseudocode doesn't. At the end of the day, you're looking at code on some guy's iPad. It's a lot easier to just understand running through the algorithm like before. I guess the idea, though, is that if we have a user ID, we have our service name, and we have the request time, we're basically keeping a map from service to user ID to a tuple of basically the current window that we're looking at and the count of requests in that window. All we have to do is get our current tuple every single time a new request comes in. Once we do that, we check whether the new request is the same minute as our current tuple, and if it is, we increase the count by 1. Otherwise, we're basically going to reset the current tuple such that the time is going to be the current minute of our request time. So, all of a sudden we went from 1 o'clock to 101. Let's set 101 to be the value of our current tuple with a count of 1. And then in terms of whether we actually want to go ahead and perform rate limiting here, we better just check whether the current tuple's count is greater than our limit. So in this case, our limit is going to be 2. Hopefully that makes sense. I think it's fairly straightforward for this one. And now we can go ahead and talk about the sliding window rate limiting. So the idea here is, if you recall from our fixed window rate limiting, if I submit another request right here, this one's totally valid, right? Forget about all these guys on the right, even though it's within a minute of these other two on the left of it. A sliding window is going to ensure that it doesn't happen. So if I just say in a sliding window rate limiting situation, all requests, if we have more than 2 requests within any minute, we have to do rate limiting, then this will actually go ahead and solve that problem. So how would we do that? Well, for starters, let's imagine that these two are valid. This is like a minute and a half later, so it's valid. This guy is also much later, so it's valid. And then even though this guy is not technically in the same minute, it is, like another 20 seconds later, meaning it's going to be the third request in a minute, and so it is going to be invalid. So how would we actually perform this type of thing? Well, in this case, we want to use something like a linked list. So let's imagine that first request comes in, right? This is going to be number 1 over here, and so we add our first node to our linked list. Next, another request comes in, and so we also add it to our linked list. As you can see, that's over here. The next thing that's going to happen, apologies for my coughing, is that we get this guy over here. And if you note, look at the time, 1:01:40. If I subtract a minute from that to 1:00:40, now all of a sudden both of these two are outside of the active time range. So we actually have to purge them from our linked list. So now all of a sudden we just have 1:01:40. Again, 1:01:40 is the only thing in our linked list. 1:01:50 comes along, which is this guy. We're going to go ahead and add that because it is within 10 seconds of whatever's in our linked list. And then finally, now all of a sudden, when this guy comes in, which is going to be, let's say, 1:02:10, we'll see that basically 1:02:10 is recent enough that neither of these guys get expired. And then all of a sudden, now if we were to add it, our linked list would be too big, and so we have to rate limit this request and say, no, it's not valid. So the idea is that every single time a new request comes in, we first purge all of the old requests from the linked list, and then after that we go ahead and add the new request to the linked list. So just to give some pseudocode to hopefully explain this a little bit better, the main idea here is that we first get a cutoff time for a given request, which is when the request comes in, minus the actual sliding window size in seconds or whatever you want to call it. And then basically the next thing that we're going to do is look at our linked list and say, hey, while the head of the linked list is earlier than our cutoff time, go ahead and remove that. So we're purging our linked list so that we only have things from the last minute in there. And then the last aspect of this is basically figuring out whether the remaining entries in the linked list are already bigger than our rate limit. And if not, we can go ahead and add our new request to the linked list. Right, so that's where we would do this. We would push our tail. And then finally, we would basically just say return whether this thing was too big or not. And that'll tell us whether we've hit our rate limit. So hopefully that part makes sense. The idea is basically just step 1, purge old entries. Step 2, add new request to linked list if it's valid. If it's not valid, then that means that there have already been too many requests in that sliding window, and you can just throw this one out, and then when a minute finally does pass that you have more room, a new request will work. You could make the design decision to actually just add it nonetheless, regardless of whether it's valid or not. But then that would mean that, say if every single 30 seconds I try and submit a new request and I have a 1 minute limit, then I'll never be able to get any requests through, as opposed to just 1 out of every 2 of them. So hopefully that makes sense. Cool. So another aspect of this is whether or not we have to consider any concurrency or threading considerations. The idea here is, yeah, we probably do. The reason being that we have a lot of potential for race conditions, right? So keep in mind that in our basically our fixed window algorithm, we are reading a counter and we're incrementing it. And so unless we're doing this type of thing atomically, which to be fair we can, but it requires locking, we have the potential for lost updates, right? So lost updates would basically mean that one thread comes in, tries to increment this guy, so it reads 1 and increments it to 2, and then another thread comes in and tries to increment this guy, and it doesn't see the fact that the thing has been incremented to 2 yet, and so it's also going to read 1 and increment it to 2. And now the counter should have been incremented twice, but in fact it only gets incremented once, and that is going to be a problem. So of course the way we would solve this is performing some sort of locking on this counter, or just running single-threaded, which is unfortunate, but there's not really any way around it. Another thing to note is that for the actual sliding window implementation, we need to be careful with our linked list. With a linked list, you can definitely have concurrent modification exceptions, the reasoning being that if I'm trying to add a new thing to a linked list and it has to point to existing elements in the linked list, well crap, now I can have two threads adding elements that point to what they thought was the head. And so as a result of that, we are in a bit of trouble. We have to perform some locking on our linked list. In most modern languages, there are concurrent linked list implementations, and we would probably want to be using one of those blocking versions. So this also applies to linked list deletes too, because it becomes a matter of, well, if I'm trying to delete the first element and you're trying to delete the first element, shoot, we might actually delete the first element twice, and who really knows what that behavior is defined as. So as far as I can tell, I don't think there's a good way around avoiding either doing things in a single-threaded manner or using locking. It's just what happens when you have data structures in memory that you need to be able to increment. So such is life. Finally, we're almost there because my voice is really starting to kill me. I'm sure you guys can hear it a little bit. We are going to do our rate limiter design. Now this one is going to be very simple because most of the work here was really, well, where do we put our rate limiter? What's the code that we run on our rate limiter? What do we actually do with our rate limiter? So the main idea, at least in my mind, is we've got some big beefy load balancer right here. It has a rate limiter cache for all of those requests, which are becoming more and more commonplace. If I'm a particularly bad actor, ideally we want that stored in the rate limiter cache so it doesn't actually have to ever reach our rate limiters over here. But basically the idea is we've got a bunch of Redis partitions, all of which are doing single leader replication, hence why we see these backups right here. And then of course what's that going to do is first we request our rate limiting service. Once we receive a response, we then go ahead and request our backend service, assuming that we didn't get rate limited. So hopefully the design is simple enough. Anyways, guys, as always, thank you for watching. Looking forward to a great 2024 with all of you, and I will see you in the next one.